So it's now time for your work later. Hopefully it's already set up. It's just a question of connecting this. Good. Go ahead. This is working. So, as I said at some stage, for those who are worried that I'm going to talk about my work, I wrote about more than 200 papers, and so I could probably go through the list here, but it would be very boring. So instead, I'd like to present you something which I think is an important topic, to which I have contributed some, and where there have been fantastic developments recently. So let me start with this video, which hopefully will work. We'll find out. Which I find is one of the most fascinating scientific visualizations, where we're traveling to the center of our galaxy, where, as you know, we have something which we think is a black hole. And so this is, one could probably say, a Nobel Prize winning video from Gillison and his team. And at the end, there's first a visualization, but then there is a movie, the extreme fast forward, where you're going to see about 20 years of real observations in a few seconds. So this is the center of our galaxy, and there are stars moving here. And you can very well describe what's happening here using Newtonian gravity. You don't need Einstein equations. So these are just Newtonian orbits of objects moving in a central gravitational field. The only place where Einstein equations presumably enter here in this picture is this place, which is presumably a black hole, and that's what, in fact, the Nobel Committee decided it probably is. And now, most of what we've seen is explained by Newtonian physics. Probably need a lot of quantum mechanics to understand the structure of stars which are there, but most of it is Newtonian physics. And so in this picture, the only place where Einstein equations would start will be this little mysterious thing at the center. And it's really hard to, it's mind-blowing that something as complicated as Einstein equations can be used at all to do any physics with, and to predict the existence of an object which, well, has the right properties, right? So, and for me, this has been always a complete mystery, how, and not only to me, but for many people before me. So Wigner was talking about the unreasonable effectiveness of mathematics. I think he probably meant effectiveness of physics, right? So mathematics as a tool to describe physics. So you already see that he was probably confused between being a mathematician or a physicist, and that's what this institute is about, right? I mean, confused about this. Of course, if you think that, like Pythagoras did, that actually, well, mathematics is the essence of things, and all the rest follows. So, I mean, so one shouldn't wonder at all why mathematics should be a useful thing to describe the universe. But I don't think everyone thinks like that. For example, well, if mathematics is really the real thing, then of course when we're studying mathematics, we're discovering things. We're not inventing anything, right? So, but Abel thinks, no, Kronecker thinks, well, no, actually integers are the real life, and so, and everything else is what we invent, right? And of course, if you, in this context, mathematics is a very good tool to describe things, right? How many people in this room, right? So this fits in this question. There is no question why should mathematics not be a good tool to describe things, right? Then if you think about the area, right? I go one step forward, one step left. I have an area of 1 step square. Well, that's, I mean, just 2 integers. That fits with this Kroneker's vision. But if I want to do the distance and the diagonal, I get square root of 2, which doesn't fit this distance anymore. So now, is this invented, or was it already there to start with, right? Well, Atiyah says something even more. Well, what about square root minus 1, right? So square root minus 1 is certainly not an integer, even though, of course, if you think about the complex plane, you could think of this as being a point with integer coordinates. So maybe this still fits in this idea that square root minus 1 is still an integer. But of course, without square root minus 1, you don't have quantum mechanics. Right? So the whole quantum mechanics needs complex numbers. So if you take seriously this idea that God made integers, and so maybe the space-time is actually quantum, everything is quantum, right? So this is the idea of making a step here and here. Is actually, I've made a lot of tiny steps, and there is no such thing as a diagonal, because it doesn't fit in an integer world. Then there should be quantum mechanics, right? But again, I mean, so then you start wondering about this square root of minus 1. Is this really an integer or not? Okay. So, but at the end, we want to do physics, right? This is the Schrödinger Institute for Mathematics and Physics. And physics is too difficult to be left to physicists, but then to whom, right? So this priest did very well, right? So this is Copernicus, and he got it spot on, but maybe not every priest had the right or attitude here. Well, there are so-called philosophers. So when I was a student in Warsaw, I had to go to so-called classes of Marxist philosophy. Now, this was in the 70s, so we were already in a period where this was not a Stalinist communism. This was not Gomulka communism, which was a rather strict one. So they understood that we don't really care about learning about Marx's theory of economy and to read the Communist Manifesto. So they let us read so-called philosophy of science by guys like that. It was unreadable and a bunch of nonsense. But fortunately, they didn't quiz us on it, right? So it was, we had to come to the class, we had to pretend we have read that, and we got a sign off and said it was okay. So don't ask me what he had to say about, but in principle, I've read some of the things that this guy had to say about it. Mathematicians, right? So that's what Hilbert meant, that we want to leave mathematics to mathematicians, but mathematics is too difficult for mathematicians, right? So Newton invented calculus. Fourier invented Fourier series, Fourier transform. Fourier was a physicist. I mean, the Fourier series and transform show up in his treatise on heat. So that was his interest, right? Exotic differentiable structures, you can think, what can be more abstract and mathematical than exotic differentiable structures? Well, they needed Young-Mills, right, who invented their fields, which were two physicists. And they needed Taubes, who was, well, he's actually a professor of mathematics at Harvard, but he started as a physicist, so, and so forth and so forth. So, and I don't need to tell you how much Wheaton contributed to mathematics as well. So, okay, but the real question is, how is it possible that complicated equations like Einstein equations can be used to describe the world? I think it's a mystery, and it's something which I've always found bewildering, and that's, you think about linear equations. I mean, a lot of them have some reasonable aspect to them. And, well, I don't know if you think about pressures or something like that, to compress something a little bit, something deforms linearly, wants to fight back, you write a linear equation, it works, right? You write Einstein's equation and it works. It just, yeah, it's a mystery. And I think that Popper would say that this is probably a ridiculous question, right? So can you falsify the statement? Is mathematics the right tool to describe the world? Probably not. Or can you? Well, let me leave you at that, and I'll be talking about Lorentzian metrics. So I'm sure everyone knows here what a Lorentzian metric is, but just in case, this is an object which determines motion through geodesics, and that's what we're going to talk a lot in what follows. And it also determines causality. That's what how the metric determines black holes, because there are these light cones which are essentially telling you nothing can travel faster than light, and so you have to travel inside these light cones, and this produces things like black hole. And we don't need to know much more about it except the Einstein equations. They're already written there. If you're very attentive, you will notice that the sign is wrong here, or Helmut's sign is wrong. And the sign is wrong because the person who wrote this equation was probably thinking about a different signature. If you multiply the metric by -1, you're going to get this sign. And the person who wrote this forgot the cosmological constant as well. But so these are the equations. That's how they look like. And so they're really unpleasant, right? I mean, if you look at about this, so this thing G, you can think of this as a matrix of 10 numbers. It's symmetric, so actually maybe is it 10? That's actually, it's still 10, right, when it's symmetric. So, and then you have to differentiate it, and then you have to differentiate actually once here and twice here, and there are all these sums, so there's a lot of terms when you do this, and then you have to make some algebraic contraction, and you have to add them, and so it is a bit of a mess, and that's why it's interesting. So that's what we do. This is something that Hans started his talk with, and this is this mixed master thing. This is the ultimate thing we would like to understand when studying the mathematics of Einstein equations. This picture here, there's a video behind it, and if I can manage to run the video, probably is somewhere hidden behind there. Oh, okay, it's here. Okay. Good. So this is the simulation, and let me explain what's happening. So this thing here is a metric on a sphere, but you don't care what it is. There are 3 orthogonal directions, 1, 2, and 3, and each of them comes with a function of time. And Einstein equations tell you how this functions should be evolved in time. If you write this metric, actually, that's going to give you an exact solution of the equation. So Hans was trying to show you how to prove things about solutions without any symmetries. This one has a lot of symmetries, and you get an exact solution of the equations. And so what you see in this video here is, write it again, run it again. It's the ratios of this function b over c on one axis and say b over d on the other. So it's telling you how the distances in various directions change with respect to each other, right? So if you move on this plane, one direction gets shorter, the one gets longer, or do something like that. And it's done in an extremely complicated way. This is something called probably chaotic billiard or something like that. That's supposed to be a good model for this behavior. Now, this is cheating, because this video is produced on a laptop just by running not the real Einstein equations, but running a hypothetical model for this equation, well, hypothesized by these gentlemen, Belinsky, Kalatnikov, and Lifshitz. And because if you try to run this for Einstein equations, it needs a supercomputer, I'm told. I haven't tried, and maybe Maciek will correct me, but trying to run this so long with a decent accuracy would be impossible. So this is a model. This is not the real solution here. And but there's a theorem about this, right? And the theorem is the version I'm most familiar with. The most recent one is by DTO. So this is actually not some approximate simulation, but this is a really what's happening asymptotically for a large class of Bianchi 9 metrics. These metrics are called Bianchi 9. And it's not even known if this is true for all metrics, right? So this is still an open problem. There was some deep contribution by Hans about this. So he was the first one to gain some insight into this problem some 25 years ago, and then so several other papers with partial results. So it's TL is the best one. This is the Belinsky-Lifshitz-Kalatnikov conjecture, which Hans already mentioned. Then this is the generic dynamical behavior of the gravitational field near singularities. Is this true? I mean, these guys was making this conjecture, I think it was complete bullshit. I mean, so, the evidence they gave for it was zero, and it was really I don't know. I have no idea whether this actually makes sense or not. So maybe one would like to prove it or disprove it. This is related to something much more serious that just, it's nice to understand the dynamics here, but it has to do with whether Einstein equations can be used to predict the future, right? So there exists examples of solutions of Einstein equation which have non-unique solutions. So and so this non-uniqueness is accompanied by something called a Cauchy horizon. And there's a conjecture formulated by Penrose. Well, for generic initial data, maximal solutions do not contain Cauchy horizons. Okay, so this is a tricky question. Do you want to die crushed in a Belinsky-Lifshitz-Kalatnikov singularity is going to tear you apart in one direction, compress in the other, and then expand in the third, and do it all over with larger and larger amplitude? Or do you want not to know what's going to happen? Because these Cauchy horizons are probably not that bad. Probably you can travel through them, but you have no idea what's going to happen after that, right? So I think there have been some trying to get a statistical answer who prefers what in the audience. And I think very often people prefer not to know than being crushed. So maybe this conjecture actually, maybe we don't want it. Maybe we love Cauchy horizons. But I mean, so if you think about philosophically, it's a question of predicability. Can you use Einstein equation to say what's going to happen in the future? And this is a way to saving it. And of course, if this Belinsky-Lifshitz-Kalatnikov conjecture is correct, then when you approach a singularity, you're going to be crushed. There'll be no Cauchy horizon. So at least a uniqueness, right? And so sometimes there are no oscillations, and that what Hans was trying to show you. He mentioned a paper by Paul Klinger where we had the first result of initial data which had no symmetries and had where you could understand in vacuum in 3+1. There were previous other results with fields and in other dimensions, but that was the first result where we constructed a family of solutions which you could understand this dynamics all the way to the singularity. And the best theorem so far in this field is the one that Hans announced here a year ago. A year ago, we had a beautiful anniversary of 100 years of Ivan Sheker-Vira, who is the mother of this field. So that was her 100th anniversary. We had a conference here. Many of you were here for this meeting, and Hans announced this beautiful result that under some technical conditions which most of them you've heard in Hans's talk, right? Then quiescent Big Bang singularity forms, right? So this is the most general result on this topic. This excludes the this BKL behavior, and well, I think that the jury is out on this BKL thing. Good, but I told you I'm going to talk about the n-body problem in general relativity. So in Newtonian mechanics, it's a Cauchy problem. So you give yourself several initial positions of bodies and their velocity. You solve Newton's equations with a gravitational field, and you get your solution on the time. Is this, does strong cosmic censorship hold for Newton? Well, probably, well, it's not clear. It's not clear, and let me explain you why. In any case, in general relativity, it's similar. You need initial data for the gravitating body and the gravitational field. And that's a little more difficult than the previous case, because in Newton's theory, you can just pick your positions and velocity as at will. Nobody prevents you to choose any configuration. Here in general relativity, you can't, and I will come to this a little later. Just to mention that I think that this theorem that we proved with Jim Eisenberg and Justin Corvina in 2010 was one of the first, well, starting at the tip of the iceberg, constructing general relativistic initial data for many body systems. You could take a configuration, a gravitational field configuration here, another one there, put them together, but very far apart. So that was a caveat. You cannot just do them close, but you can put them far apart, and now you can start Einstein equations and see what happens. And there will be a beautiful development about this very shortly, which I'm going to discuss, well, recently, which I'm going to discuss very shortly. But so you could also ask the same question: can you put several black holes at various places and get initial data for this? This is what numerical guys do. They put numerical black holes on a computer, they evolve them. The question is, are there such data? Can you prove that things like that exist? This is mathematical physics rather than numerical physics, right? And so here, at the time, we had a little before, actually, we had a theorem about black holes, to which I will come, later. But then, what about gravitational physics, a la Newton, right? So this is a beautiful result for Mr. Shia, two papers a few years apart. So what is the question, right? So you take an initial configuration of Newtonian gravitational bodies, you let them run. Do you get a solution for all times? For example, you can, if you take two and you shoot one on another, obviously it's going to stop when they hit. And so there are configurations which don't exist for all time. But now, if you have two bodies, the configurations which don't exist for all time are actually zero measure. It's in this set of initial data, because as soon as one has an angular momentum across the other, it can never hit the other one. So the only configuration which hits is the one which has zero angular momentum, and that's finished, right? So the set initial data which does not have global existence is zero measure, and so you can think that this is a proof of cosmic censorship in Newtonian gravity. Well, but what about more bodies, right? And so this is actually a configuration of 5 bodies. There's, I think that these things, you can think of them having large masses, and this one having a small mass. This is called the messenger. And so these ones are essentially symmetric. And so this messenger comes here, and you arrange things so that when the messenger arrives here, it gets kicked backwards. Well, of course, it doesn't collide with any of the matter fields, but it gets kicked backwards and is sent back to where it came from, but much faster. Of course, these things have to the orbits have to shrink by conservation of energy, right? So they've given some energy to the messenger, so they have to shrink. And there's a kick, so they have to go down. And so you arrange things so that the messenger comes here, gets kicked back, comes here, gets kicked back, and so forth. And he proves that you can arrange the initial data so that this thing flows into infinity in finite time, right? So this is probably an example of a Cauchy horizon, because there's no collision, right? These are called collisionless singularities. There's no collision. Of course, these things, this small system gets tighter and tighter, but so in finite time it flows to infinity, or what happens to infinity is a different story. But so Newton's theory breaks down, and the question is, well, is it for very special configurations? Is it for, or maybe not? And this is still not known, right? So this is an open question. This question of collisionless singularity was already raised by Pain-Levé in 1887, and he proved that in n equals 3 this does not happen. So there are no such things with 3 bodies, right? So he conjectured that this is possible with n larger than 4, and indeed Xia proved this for 5 bodies. And 4 years ago, Jinxin Xue showed that it works also for 4 bodies, right? So this is a beautiful recent progress in Newtonian dynamics. He actually proved that there is a counter set, technically, of initial data which leads to 4-body non-collision singularities. That the dynamics is much more difficult to understand than the 5-body ones. And again, the question, I think if you're thinking on the plane, then this is a counter set of 0 measure. And I think he says that this is a counter set of 0 measure. But of course, if you think about non-planar collision, it says it's open, right? So it could still, the measure of the initial data which leads to such things is 0 measure. Another example, this one is easy to understand by Gervais, but he needs a lot of bodies, right? So this is actually 3 n bodies, because he has 2 bodies circling together, and the messenger is traveling like that. And so this messenger will come here, will get kicked, will be redirected here. When it gets kicked, this orbit shrinks. Because there is a conservation of momentum, then this system has to be sent away, and everything is done in a symmetric way, so that these circles get larger and larger at every passage of the messenger in the center, and in finite time the thing goes to infinity. Well, in Newtonian mechanics you also have nicer things than collision singularities, and there are things which you will not have in general relativity, because a system like that would be radiating, and if it's radiating, then it's going to lose energy, it has to shrink, right? But this is allowed by Newton's equations, and then there is this version, which is kind of cute, where so each body moves on an 8, well, there is 3 bodies on an 8. Note that, well, all 3 bodies are on the same black 8, right? But there's another 8 formed by the by these 2, right? So the green one and the blue one. So this is on a plane, and you can see many more of these on this website. For example, you can have a periodic configuration like this one, probably somewhere behind. Get there. Maybe just close this, maybe. this one. Apologies. So a few days ago, I crashed on my bike. I use my face as a support for crashing. So it's a little better now. So I mean, a few years last week I would have had a red nose like that. But also my computer crashed. So I destroyed my screen, and I have to use a guest computer. And obviously, it's not working as good as it was planned. Let's try again. Way to start this video, this one. Okay, good. So this is a acute configuration where, again, you're just solving Newton's equations, right? For three bodies, same masses, and there is a space curve on which all the three move together, rather complicated, right? So this one is, they're all moving on the surface of the sphere, and I think it's very pretty how they get together and form a little circle, and then it opens up, and another one, and so forth. Right, so each of them moves on one curve. It's periodic, right? And the whole thing is periodic. So you get a lot of interesting configurations like that, which were certainly not known until these papers by Schrödinger and Montgomery, which proved that there exist many configurations like that. So again, this is Newtonian gravity. Nothing like that can happen in general relativity. And now if you want to go to a gravitational many problem with quite a few more bodies, well, there are these galactic dynamic simulations, and again, it doesn't seem like it wants to work. Let's see. Okay, so here you are. So now here you have really a lot of bodies floating around. This is a simulation of how a universe will presumably evolve, right? So you have, each of these is a galaxy which is comprised of many, many single objects. This is solved on a computer. This is solved, this is Newtonian dynamics. So there is a component of general relativity here in that, well, we expect now that every galaxy has a black hole in its center. So they are modeling a black hole, black holes which are out there by some exchange properties with the medium, right? And they're never solving Einstein equations. And we are very, very far away from being able to solve Einstein equations in certain contexts. It's probably not needed anyway at this densities. But at some stage, you'd like to be able to input something from Einstein equations here, and that's not something that we would be able to do in a near future. This is like a simulation by this team, Illustrious project from the Max Planck Institute in Garching. So good. So far for fun, and I'm going to, I don't know how much time do I have. Do I have some time left? Or it's, yeah, so just a few technical things, right? So I told you two-body problem is a Cauchy problem. Initial data, general relativity is the same. You have to give an initial data surface here with data, and you try to run the equations. There's a difficulty called the constraint equations. And so for those who know will know, who doesn't know will probably, there's not much point to spend time on this. But so this is an equation for a metric, and this is an equation for the time derivative of the metric. Right? So give yourself a metric here and its time derivative, and they're supposed to solve some Einstein equations, and there's some basic fact which actually started our understanding of this. First was Darmois, who showed that these equations propagate in the analytic case, so you can just really get a system of evolution equations out of Einstein equation, and then Ivan Choquebras showed that you can do it in smooth case, and then, or not smooth, but see something where it's good enough, and then So then when mathematical general relativity was really born. And right, but now we want initial data for a many-body problem, right? So we want to put things together, and in particular, maybe for many black hole problems, and that's the way to do is something called space-like gluing. So the problem is that if you want to solve the Newton's equations for two objects, well, you give initial data here, you give initial data there, and things propagate. Now here you have these constraint equations which prevent you to put things together because these are equations for on the whole surface that you're working here. And so what you have to do is understand this, and there is a beautiful method which is the gluing. So you cannot just superpose data, okay? So take Maxwell equations, take initial data, add them for two configurations, you get new initial data. Here you cannot superpose them in a naive way, and Convener and Schoen invented this gluing method, which allows you to put things together, and it uses various properties of the equations and so forth. And this is actually the state-of-the-art variation on Convener-Schoen is I give you 25 black holes, and I find initial data which describes those, okay? So this is his theorem 2 years ago. So we take a vacuum initial data set. There's a technical condition which says there are no killing vectors, which you can just ignore. And what he says that you can take a black hole. Here in this case, it's called a Kerr black hole, but who cares? So just you take initial data for a black hole. So let's say it looks like that. So roughly speaking, so this is a black hole. And you can take your other initial data set, and you can find a new set which has whatever you had before outside. And here inside, it's going to have a small version of this one, right? So if this, say, has a mass m and angular momentum a, you'll get a scaled black hole which will have a small mass and a small angular momentum. And but this you can do everywhere, right? So there is a smallness assumption. But so you can do it for one. That's the first theorem, right? That you can construct the data for one black hole. But you can repeat this. Once you can do it for one, you can put as many as you want. In 2002, we wrote something similar, but in very special configurations. So it was nowhere as nice as what Peter Hinz is doing. But this is now the main theorem, and that's why it's just a beautiful, really progress in general relativity. So for the paper is out well in August. Zoe was kind enough to mention the CES meetings that we have every year with young people giving talks, and we always have one or two senior people giving talks. And so Piotr was presented this result at the CES meeting. So I'm very proud that this theorem was first let available to the world on a meeting I organized. But so then the paper is here, and what he says is the following: that if you that you can control the evolution now, right? So not only you have initial data, but you take your initial data set, you put your black holes here, and they're traveling in some directions, and they have a small size of epsilon. Then you can construct a solution which lies along a geodesic for a time at least 1 over epsilon. So the smaller you make this black holes, the longer you know that the solution exists, right? So then you gotta get a really many black hole space-time, which with this remarkable property that black holes travel of geodesics, right? So this is something which was kind of an axiom of Einstein's theory that objects move on geodesics. And in some sense, it can be derived in some situation from Einstein equations, but mostly it's a heuristic argument. Now here he actually justifies this, right? So he proved that you take a geodesic in your space-time, then you can construct a new solution in which black holes are traveling around this, right? So this is the picture where, well, this is well, you scale thing, and well, if you scale it, you get something like that. But so this is the interesting part here. Of course, suppose you are already in a black hole space-time, say in a Kerr space-time, then you can choose in Kerr space-time a geodesic which enters in a finite time inside the horizon. And therefore, by his construction, you can get a black hole which merges with the original black hole in a finite time. And then you don't have to worry about what's happening after that, because once you've crossed the horizon, you can now study the evolution of your metric outside of the horizon. And now we have stability theorems for this. There's a beautiful theorem by Kleinenmann, Scheftel, and Georgi, which says that small perturbations of a black hole space-time, Kerr space-time leads to a Kerr space-time. So since this is a small perturbation, by his construction, once this guy has entered here, you get a global solution which contains one black hole at the end. And of course, you can iterate this, right? So you can get a small guy merging with a larger one, and this larger one merging with a slightly larger one, the third one coming from the side, and this going here. And so this really opens a new world as far as mathematical relativity is concerned. So this is all I wanted to say about the many body problems in general relativity. This is the landscape of my field, right? So I've been fortunate to be able to work on this for many years and to solve some of the fascinating problems that are here. So mathematical general relativity has essentially, from my perspective, three legs: Lorentzian geometry, which is kind of the language on which everything is based. So two languages are Lorentzian geometry and PDEs, right? So and then, but then there's the theory of stationary black holes, which has an importance of its own, and there's the Cauchy problem. Lorentzian geometry has a funny properties. It has a smooth part, and then there are metrics which are not differentiable, and opens a new world. And we have Kunziger, Steinbauer, our expert. They really opened up this field of metrics which are extremely unpleasant and probably, well, I can think that I probably opened it up a little bit, but then make it worse. So there's this whole theory of stationary black holes, which has various branches, and there's a Cauchy problem, Cauchy data, gluing, space-like gluing, characteristic gluing, global charges. Helmut was kind enough to mention my work on the mass. It appears here. Strong cosmic censorship. Well, I wrote a book about it, but I never managed to do this. This is one of my failures, just not to be able to do anything about BKL, even though I spent quite a bit of time on this. And so this is the landscape, and I'm happy to have contributed to the red things here, and I hope to contribute some more. Thank you.